Please get seated from this side. Yes. So, we will continue our study of the Prolog programming language. So, in the last class we had introduced the basics of the language. To give you a brief recap, we can have in Prolog facts, ground facts specified as predicates like this, and also we can have rules like this likes Harry X if likes Ron X, and then we can deduce goals like likes Harry Broom, which is a ground goal, ground predicate, and we just have to find out whether this is correct or not. So, we have to find out whether likes Harry Broom can be inferred from the set of facts and the given set of rules. We can also give queries which involve a variable, in which case Prolog will find out all instantiations of the variable which satisfy the predicate. Right. So, for example, here it will find out all instantiations of y which satisfies likes Harry Y. So, for example, y will be instantiated to Broom as well as school in this program. And then we had also seen that you can actually give a goal where all the arguments are variables, in which case it will find out all ways of satisfying that predicate. Let us look at recap what we had studied on lists. We had seen that lists can be written in several ways in Prolog, and lists are in fact the only kind of data structure, if we may call it that Prolog supports. So, the lists are of the following types. You can have item 1, item 2, etc., or you can have head followed by tail. You can have item 1, item 2 and then a list. So, whatever comes after this bar is another list, which is the rest of the original list. And then we had seen that items in the list can in turn be lists themselves. Right. So, after this what we are going to do is we are going to study several examples of Prolog programs, of which we had started seeing two programs, namely membership in a list, which was like this, that x, this member x for x, this member predicate has two arguments x and y, and is true if x is a member of y. And when we refer to member of y, we just mean that at the top level list. So, we assume that in the predicate member x y, y is a simple list, or we are actually finding whether x is an item of the list itself and not any sublist. So, under this we had two predicates, one is member x comma tail, which is satisfied when the first element of the list is x, and then we have member x comma head comma tail if and only if member x tail. Right. So, if the first predicate fails, that means that the head does not match with x, and therefore, we recursively find x in the tail of the list. Right. It is a member only if it is a member of the tail. Right. Then we had seen concatenation. Did I do this in the last class, concatenation? Okay. So, to quickly recap, concatenation is in two predicates. The first one says that if we concatenate an empty list with L, then we get L, and the second rule says that if we concatenate x as the head and L1 as the tail with another list L2, then we will get a list x with L3, where this x is bound to this x. So, the first element of this list is the first element of this list, and the concatenation of L1 and L2 will give us L3. Right. Yes. Bracket? No, L2 is a list, it is already a list. See, this concatenate predicate has 3 arguments, all 3 are lists. Is that clear? No? Give an example of how this will work. Okay. Let me first take down the predicate concatenate this. L1, then L2, okay. Now let us first take an example where we are looking for, say, the truth of the predicate. So, we are given 3 lists. So, we are given, let us say, AB, right, and we are given CD, and we have ABCD. Suppose this is our goal. Okay. So, what is Prolog going to do? It is going to try to match this with the rule heads. So, the first rule head is this, which is a ground fact. Does this match with this? Is there an unification between this and this? And the answer is no, because this empty list cannot unify with this list which is non-empty, right. So, this unification will not work. So, it is going to try this one. So, if we unify this with this, then here x will be equal to A, B will be the list. So, if we unify this with this, then x will be A, just the element A, L1 will be the list B, L2 will be the list CD, and then x will unify with A, right, and L3 will be the list BCD. So, once this head matches, the sub goal that will spawn off from this will be this one, conc with L1 which is B, right, B, list B, yes, L2 which is right, and L3 which is right. Now, this is our sub goal. Now, with this sub goal we will again try to do the same thing. Again it will not unify with the first rule head, because this is still not an empty list. So, again it will unify with the second one, and that is going to spawn off another sub goal. And what is the new sub goal going to be? It will be conc empty, then CD and CD, right. Then it will try to match this again with the 2 rule heads. So, this time the first rule head will match, because this empty list unifies with this empty list, and these two, this L can unify with these two because these two are identical.
The Prolog can identify
Right?
the whole list at our instance only.
When they are equal, it can identify. Okay. So, therefore,
Sir, but to test that equality also, it should go step by step.
it will do all that. See, the point is that here is a binding, the binding between the second and the third argument of this predicate. So, it says that whatever you instantiate the second argument with will also have to match with the third argument for this rule head to unify with whatever you want to unify it with. So, for example, if we slightly modify this case and look for matching, say suppose we try to check whether conc say A and B will work or not, right. So, again if we try to do this, we will first try the first rule, it will not match because of this, it will not match because of this and also because of this, because these two will not unify, right. So, therefore, it is going to try the second one, and when it tries the second one, again this binding cannot be satisfied, the head of the first argument and the head of the third argument are not identical. So, therefore, this rule head will also not match, and when both of the rule heads do not match, then you will return false, because there is no other option to unify this one, right. If you had something like say AB with A say D, let us see what will happen here. It will not unify with this, so it is going to try with this one, and then when it tries with this one, now this binding is there, right. So, it can unify with this, and the unification will give, it is going to give L1 is empty list, L2 is the list B, and L3 is the list D, right. So, the sub goal that we are going to have is, so once it matches with the rule head, this becomes a set of sub goals. So, if we can prove these, then we are done, right. So, if we try to prove this, then what is going to happen? We will try to prove empty, L2 was B and L3 was D. So, we go back and start again. This time the first argument unifies, but these two do not unify, because if I unify one with L, then I cannot unify the other with L, right. So, this binding cannot be satisfied by this predicate. So, therefore, it does not match with this rule head. We go to the second one, and in the second one the head of this one is empty, whereas the head of this one is D. So, therefore, again this binding from X to X here cannot be satisfied here, right. So, therefore, it does not match with the second rule head either, and that is when we declare that it is a failure. Is that clear? Just to round it up, let us look at one more case where we have a free variable. So, suppose we say that what is going to happen if we have conc of A, right, with Y, and we have AB. Let us see what is going to happen. It is first going to try this one, it will not unify because of the first argument, it will try this one, right. Now, let us see how the unification proceeds. It is going to try to unify the head of this list with this X here, right. So, head of this is A, and then it will check out the binding with the third argument, and yes, the binding can be satisfied because this head is also A. So, therefore, it is going to create a unification which is as follows: L1 is the empty list, right, Y is, rather L2 is the free variable Y, and L3 is B, the list B, right. Now, once we have this, we will try the sub goal empty y B. Now, again it will try with the first one, this can unify with this, right. Now, this can unify with this, and we can do the unification if we unify y with the list B. So, if we substitute y with the list B, then these two will unify, right. So, therefore, Prolog will print
case it doesn't unify with the first two. So
in which case in the first round? Yes.
So won't it proceed to unification with the second root?
No, it in the first round or in the second round?
In the second round.
In the second round it is unifying with the first one only. We are unifying with this only.
Sir, but it is giving me cases where I will unify with it.
Yes, it is going to give me a instantiation of y which is able to satisfy this predicate.
So won't it try for the second rule that whether there is
Oh, after this, yes, it will. So it is not done yet. After printing this, it will still try to match this with the second one, right. But the moment it tries to match it with the second one, this empty list cannot unify with this, right, because here we have x, here it is empty, right. Yes, but then your L1, no, this is not going to unify with this one because both are empty, then both has to be empty. This signifies that x cannot be an empty element if you write it this way. X is not a list, x is an item, and when you are talking about empty, it is the empty list. So x cannot unify with an empty because there are two different types. Empty is a list type and x is an item. Okay. Is this clear, the way in which Prolog is working backwards?
Initially we declare the variables and how y is distinguished. How does it as a variable and
Okay, it doesn't distinguish between there is no explicit declaration as such, right. But when you are specifying that x bar L1 like here, right, that the semantics of the language tells us that this is a list and this is the head of a list. So it is an item. Okay. Let us do a few more examples and try to work out a few yourself, right. So let us see. Okay, so suppose we are given a list and we want to add an element to the front of the list, right. So okay, so we have text please, text please, text please, text, yes. So we have add an element x into a list L to get another list, this thing, right. How are we going to write this? So add x to L1 to get L2. That is the same in Prolog as saying that the concatenation of x and L1 is L2, right, except that here unlike the list concatenation, here x is just an item, and we want to have a list L2 where x is the head and L2 is the tail, right. So, how are we going to write this? Try writing it. Firstly, write the ground part of it. So the termination condition for the recursion. Add x L bar L, isn't it? Anything else needs to be done? That's it. That's it. Nothing else needs to be done, right? What about deletion? Suppose we have to write deletion of x from L1 gives L2. Deletion of x from L1 gives L2. How are we going to write it? No. Here x is not necessarily the front element, it is not necessarily the head, right, but it is some element of L1 and we want to get L2 after deleting it. If L1 does not contain x, then L1 and L2 will become identical. So, again the termination condition will be what? When we find, right. So, that is the termination condition. So, let us first write down the termination condition. So, the predicate for the termination will be delete x comma tail and tail. So, if x is the first element of the list, then after deletion we get tail. Otherwise, what should we do? Otherwise, we have to look further into the list. We just have to skip the head and look for the deletion in the tail, right. So, we will write delete x and then y tail, right, and if the first element is not x, then the first element of L1 and the first element of L2 has to be the same, right. So, therefore, we have to put y again here. So, this is the binding, right, followed by some tail 1, okay. So, L2 some other list, right. So, this if delete right. So, we are now beginning to get a hang of how Prolog works, right. If L contains in this case it is going to remove only one of them, yes, it is going to delete the leftmost one, but you can always write another predicate that will delete all instances of this thing. So, that is a nice exercise. Try to extend the delete predicate so that it deletes all instances of x from the list L1 to return the list L2.
extend till means the base case will be delete x and x.
So you have to continue up to you yes, until you get actually. So this empty list check will come before this, right, and here after checking this the slides please, the text sorry, yes. So after getting this delete this thing, right, so this will continue. So this is not going to be the termination criterion anymore. So once you get this thing, you will also have to add here that delete. With this you have to then add delete x with yes.
So x empty list. X and empty list.
No, that will be the termination criterion will be that when we have delete x, right, and we have the empty list here and the empty list here, right.
Sir, x there.
No, what if the last element is not x, right. So you have to go to a point where you are deleting x from an empty list and the result is also an empty list. That is going to be the termination criteria. When you are here that you have found one instance of x, right, then you still have to delete. I mean this is not yet tail, it is some tail 1 still, because it is not yet deleted all the elements from x, right. So this is going to be some tail 1 and you will have to do delete tail 1, right. So this is another rule that is going to come up. So try to write it out, deletion of all instances of x from L1 to get L2. Now let us look at another case, sublist. The sublist S of L, concatenate L1 L2 to get L and concatenate S L3. Can you follow what is this happening? We want to find out whether S is a sublist of L, right. So that is going to happen if I can find out two lists L1 and L2 such that their concatenation gives L, right, and concatenation of S with some L3 gives us L2, right. Now see, why is this so complex? It is so complex because the lists elements can in turn be lists, right. So we are just trying to find out whether S is a sublist of L. So it could be within L, it could be inside some level of nesting, right. So what we are trying to do here is we are trying to see whether if it is sublist, then there is some S, if we concatenate S with L3 we will get L2 and L2 and L1 will give us L, right. So at one level of nesting. So let me execute this with one example. Let me first take this down. So sublist S L if concatenate L1 L2 L and concatenate S L3. Now this concatenate predicate is already defined previously, so I am not repeating that. So let us say that we want to find out whether so here when I try to match with this, then what is happening? Right. So L1 is D, L2 is ABC, right, and then when we come here try to unify with this, then what is L3? Right. So roughly this is the way in which the final instantiations are going to take place, but the question is how does it know that it is going to break up in this way? So it does not know. So what it is going to do is it will try all kinds of instantiations progressively until it hits upon the right instantiation and is able to match the goal, right. Let us look at permutation. So our objective is to check whether one list is the permutation of another. So permutation of the empty list is the empty list, and then observe this one. Now let us see what is the second rule telling us. Second rule tells us that, so the first argument is the list X and the second argument is the permutation P. The first argument is this list argument and the second argument is the permutation of the list. So we say that this P is a permutation of X bar L provided that L is a permutation of L1, right. Okay. So what is happening? If you take L1, L1 is a permutation of this remaining list, right, and then we can insert X at any point in L1 and then we will get P, right. Okay. Right. Now let us see with again with an example that how does it work out this thing. So suppose I will shortly define it. Insert is easy. Insert means that basically that X has to be a member of P and the remaining elements is going to be identical to L1. So in other words, if you delete X from P, you should get X1 L1. If you delete X from P, you should get L1, right. Anyway, so let us say that we are looking for the goal where we are looking for permutation say So, if you look at the second rule here, then it's not going to match with the first rule because the lists are not empty. It is going to try with the second rule, where it is going to instantiate x with A, right, and then BCD, right, is our L1, is our L, is our L, and our L1 is the list D, C, B, and when we insert x in L1 here, we get P, we get this. So, basically it finds out at which point we should insert this, so that we get this, and if there is no point where inserting this is going to produce this, then this is not a permutation of this, otherwise this is a permutation of this.
How does it unify L1 with P or DCB? How does it unify this?
See, at this point of time, it does not know what should be the value of L1, such that inserting x in L1 produces the permutation, it does not know, right. So, what it is going to do is, if you look at the way in which the binding will propagate is, it will start with the final permutation that you have given here, because you have given it here. So, it is going to start with this, right, and it is going to delete from this A, right, and so it is going to find out DCB. If you leave, yes.
How does it know that this satisfies permutation of L from L1?
Which satisfies? No, that has to be checked again recursively. Recursively, that has to be checked.
And A it will find by a linear scan through that list.
Which one?
A, there is
Now see, that depends on how you have written insert. So, it is going to try to match. See, what is the, it is going to go strictly by sub goals. So, let us see what are the sub goals that it will generate. So, the moment you give something like this, it will first try to match this rule head with the rule head of your permutation program, right. So, it will match x with A, it will match L with BCD, that is sufficient to unify the head, right, and it will match P with D, C, A, B, right. So, now what are the sub goals that it has? It will create two sub goals. One is permutation of L, which is BCD, with L1. Now, what is L1? We do not know yet, right, and the second sub goal will be insert x, which is A, right, again in L1 we do not know yet what is L1, but it should produce D, C, A, B.
So, instead we can't we simply use the delete function and we put
We can write it also using the delete function, right. Now, what we do here is, when you have these two sub goals, then we can process these sub goals in any order, right. But what Prolog will do is, Prolog will go depth first. So, it will first try with this one, right. So, when it goes depth first with this one, this is again going to generate two sub goals. One is permutation of CD to give some L1 hat, because this is at the next level of this thing. This L1 and this L1 are not the same, right, and it will also generate the sub goal insert B No, L1. Yes. Right. So, from this level of recursion to this level of recursion, this is the binding that is getting carried down. Right. Again, it is going to go depth first, so it will try this sub goal first. So, in this way it will continue until you hit upon the empty list, and then you will backtrack, right. So, try to just follow this sequence of instantiations and work out the complete derivation tree for permutation, right. That is going to give you enormous insight into the way in which Prolog will work. And I suggest that you try out with two scenarios. One is where your lists are already instantiated. So, you are given two instantiated lists like this, and take another scenario where the second one is a variable x. So, in which case Prolog will print out all permutations of ABCD, right. Is that all right? There is another way of writing permutation, and that is using delete, as you were asking just now. That you can write also in terms of delete, where you say that okay, L is a permutation of x bar p, provided that by deleting from L, if we delete x, then we will get L1, and then L1 is a permutation of p.
So, why to change the order?
Which order?
Why to write permutation first and delete?
You can write it in that order also. See, the problem that will happen here is that if both are uninstantiated, I mean if L is instantiated and this is uninstantiated, right, then P is not known at that point of time. So, when you try this one first, your L1 is not known, P is not known, right. So, you can potentially go into an infinite sequence of infinite recursion. You need this one first to get the binding of L1, you to get an unification with L1 which you can carry up here. Otherwise, your L1 and P will both be variables and you can go into an infinite recursion. Okay. So, that the sequence in which you specify the rules and the sequence in which you specify the sub goals is important in Prolog, because Prolog is not doing a resolution search like we were doing in when we worked it out by hand. It is going to do a depth first search among the sub goals.
So, can we have the predicate delete inside the permutation? For example, suppose we have permutation bar x is x bar L comma p. So, we can write permutation L comma delete x comma p.
No.
X comma L comma p. X comma p comma L. Sorry.
So, you want to treat delete as a function which is going to return a list, right. You can do that, but then you have to have predicates which defines the delete function, right. That is also quite complex. That can also be done, but it's quite it's going to be quite complex, not very straightforward, because Prolog supports functions, but you have to define those functions within predicates, right.
So, can you write the rules using member function, member predicate? Like every member of the L1 is a member of L2, and if every member of L2 is a member of L1, then they are essentially permutations of each other.
You can,
But how do you write the R part?
but you have to also ensure that they do not appear more than once. Yes. Yes, please. But see, member means what? Suppose you have 3 A's here. Okay, I was referring to permutations where you do not have repetitions, right? But if you had 3 A's here and 1 A here, then each of these A's is a member of this, and this A is also a member of all 3 of them, right? But they are not permutations of each other, right? That is number 1. Even if you allow multiple permutation with duplications, then also the number of A's here and the number of A's here has to be the same, right. So, just by checking membership we may not be able to do it so easily. We have to also check the number of occurrences of them. Had it been sets, then it would have been fine, but these are lists, not necessarily sets. Okay, Prolog has some arithmetic and logical operators. So, we have plus, minus, star, division, mod, and the is operator forces evaluation. So, if we write that is x is 3/2, that will be answered by x equal to 1.5, because what it is going to do is it will evaluate 3/2 and produce x equal to 1.5. We also have the following logical operators. We have greater than, less than, greater than equal to, less than equal to. Then we have equal and not equal, right. Right. We will see some examples with these. GCD of two numbers, GCD of x and y is z. The predicate is GCD of x and y is z. So, if we have GCD x and x, then that is x. And can you recognize this method? Yes. So, GCD of x and y is d provided x is less than y, y1 is y minus x, and GCD of x and y1 is d, right. So, it is a familiar recursive way of computing GCD, and that is being just coded in Prolog here. Length of a list. So, here actually what you should note is in these two that we have used the less than operator here, and we have used the is to evaluate the value of y minus x here. Similarly, here we are using the plus operator and the is operator to evaluate that. So, what is happening here? We are checking the length of a list. So, length of a list which has some head. So, this underscore here means that it is a wild card, it could be anything. With tail we will have size n, this list has size n, provided that the tail has size n1 and n is 1 plus n1. And the length of the empty list is 0, right. This thing here underscore, this underscore, oh, it means you can replace it with any variable also. It just means it is a wild card, you can instantiate that with anything, x or head, whatever you can write. This is a standard thing in Prolog actually, that is all, nothing special, just another variable, right. If in GCD if your initial x is greater than y, right. So, in for this to work, you have to basically put the smaller one on the as the first argument and the
Then the second one should be GCD Y1.
yes, yes, yes.
After subtraction, if it x becomes larger, the first x becomes
I think we have to put another rule, yes, where the you take care of the opposite one. I think we need to have another rule which just interchanges x and y here. That will take care of the remaining part, isn't it? Oh, okay, length of list is fine, right? Try to figure out with an example how it will work when you give a instantiated set of values or when you do not give any the value of the length. So, it should return the value of n if the length is not given. Right. So, we have a few more problems, but I guess we are running out of time. So, we will do it in the next class. I was hoping to finish Prolog in this lecture, but okay, I will need one more lecture. Okay, I think that has created a lot of confusion. This underscore here, replace it by any variable of your choice. It is just some wild card, that is all. You can replace it with x, anything which is not here, take that variable. We use that usually when the value of that is not important. So, it does not have to bind with anything else. Say for example, if you put head here, then in the rule body head is not binding with anything, right. So, it is something which is not important. So, we just put this signal to indicate that it is a wild card. We do not need to bind that with anything. Okay. If in the left hand side, if you yes, yes, it means and of the sub goals. Or is between the choice of the rules. So, you can have more than one rule with the same rule head, and that is a choice between the. So, it will first try the first one. If it fails in the first one, it will try the second. That is where the or is. So, if you just if you draw the entire derivation tree of Prolog, you will get an AND OR graph, where the or is choosing which rule head to unify with, and once you unify with a particular rule head, then the set of sub goals that you create is the set of, yes, it is the AND node, right. So, it is a pure AND OR graph that you will get as the derivation tree. Right, we will start with our last lecture on Prolog. So, I hope to finish off with Prolog in this lecture, and in the next lecture we will cover up some leftover topics from the previous chapters, right. So, I guess that that will bring us to what we actually want to cover before midsems, and then we will decide that what to do after mid semesters. Right. So, the chapter that I want to start today is on exercising control over Prolog. So far we have seen that Prolog has a well defined way of deducing new clauses from the existing ones. So, namely it does backward chaining, and within each rule it will go left to right among the sub goals and do depth first resolving of the goals left to right, and it will carry the bindings from left to right also on each rule. Now, today what we are going to see is that Prolog does allow us some constructs to tamper with this control. So, we will study those things, and that will bring us to the end of what we should know about Prolog. So, I will take one example first to recap the control flow that we have in Prolog. So, let us say that I have a program which is like this, that I have R A, then S B C, These are 4 ground facts, and then we have the following rules. This is just a token example that I am constructing. Now, let us see the control flow that will take place for Prolog. So, we will right, and then there are 2 options here. I can match it with this rule head or this rule head. So, let me create 2 branches. So, if I take this branch, if I match it with this, my sub goals will be 2, namely, so let me number these rules. So, this is say 1, 2, 3 and 4. So, if I choose 3 to instantiate PAY, then I will have 2 sub goals, namely QX and RY, and I am using the AND because both of these will have to be solved in order to solve this. On the other hand, if I use this rule, then it would have taken 2 sub goals again, and those sub goals would be Rx and SXY. And whenever we have 2 sub goals which have a common variable, there is a binding between these variables. So, there is a binding between this x